In this video we are going to discuss Prac class 9a. So it is about Newton's method. So let's recap what Newton's method is. Suppose you have a function, so you are going to find its exact root using Newton's method, right? So here you can see that the x is a root, exact a root here located here. So we are going to find that one approximate solution, approximate root to this exact one, right? We are starting off any point from, let's say we are starting from here, right? So here, right? So this is our x naught or P naught, right? This is your initial point, right? Now in Newton's method, you consider the this function should be differentiable, otherwise you cannot use Newton's method. If function f is differentiable, then we can use Newton's method, right? So if after choosing the initial point, the starting point, you consider the derivative at that point. So here look at this. So this is the tangent line at that point. We draw this tangent line and we consider the point. So at which this x-axis and the tangent line meet, right? So now, so look at this one. This is our initial guess, and now this is the first iterative. And now what we do here is we consider a tangent line at this point. Here, look at this here. So now we do iterate again. We consider the tangent line at this point, and we consider the point at which the x-axis and the tangent line meet, right? So we keep doing this one until we reach the exact root of f. So here we can here we get an approximate solution. We don't get exact one, right? Sometimes if we are lucky, we may get exact, but most of the time we get an approximation to exact root, right? So we keep continuing this process until we reach this derivative to the exact solution, right? So let's look at the algorithm, right? So if you know function f, then you can find the derivative of f because f is differentiable. So you can find the derivative of f at this point. That means you know the slope at this point. Then you can find the equation of this straight line, right? Then, so that means you know any point on the straight line. Now you find the point at which the straight line and the x-axis meet, right? So that's how you get this equation here. The second iterative, this is the initial guess. The first iterative is equal to this one, the initial guess minus f of x, the initial one, and f prime of initial one. Now we do this, we keep we do this process again, we repeat this process again. This is the first iterative. Then we can find the second iterative, right? And this goes on, and this is the general one. n plus 1 iterative is equal to nth iterative minus f of nth iterative divided by f prime of nth iterative. So this is the formula for Newton's method, right? Let's apply this. Let's apply this method to a problem. Here, look at this. This is our node. This is our initial guessed. This one is the initial guessed, and this one is the first iterative. And second, then we find the second iterative using the first iterative, right? Using this formula here, and this is the general recurrence relationship, the Newton's method, right? So let's look at this problem here, right? So this is related to the first question in our prac class. So use Newton's method to find an approximate solution to this. So here in our prac class, do you remember, find an approximation to 3 cube, not 3 cube, 3 1/3, 3 to the power 1/3, which is correct to 8 decimal places using Newton's method. So definitely you have to consider this polynomial. If you want to find an approximation to this, then you have to consider x to the power 3 minus 3. So right, so you should consider this polynomial, cubic polynomial, right? So we know that 3 to the power 1/3 is a root of this polynomial. So now we use Newton's method to find that root. That means find an approximation to that root, right? So this one also similar to that. So here we find an approximation to square root of 2. In this case, we have to consider this quadratic equation, x squared minus 2. So we know that square root of 2 is a root of x squared minus 2, right? So we use Newton's method to find an approximation to square root of 2, right? So now this is our function. So this is a continuous and differentiable function, right? Continuous and differentiable function. Now look at this function here. This function is a polynomial, second degree polynomial, a quadratic equation. So square root 2 is a root of this one. Now we are going to find an approximation to square root 2 using Newton's method, right? So here this is a continuous and differentiable function in real line. So you can find the first derivative of f by differentiating f with respect to x, right? Then so now we use this equation to find the next iterative, or you can this one here, right? So what is our initial guess? So we initially guess this one. We start with this point here, right? Then we can compute the first iterative. This is the initial one, initial point. You can substitute this one, you can plug this number into the equation, then you can find the first iterative. This is first iterative. Then we use this first iterative to find the next iterative, which is this. We keep doing this here. This is the second iterative, and third. So this is so here we have 8 decimals. 1 2 3 4 5 6 7 8. This is correct to 8. So this has 8 decimal places, right? And this is the fourth one. Right. So here this is the second iterative, and for third iterative, this one is the third iterative. They'll look at these decimal places. Here you have 0.416666, something like that, but here changes. Let's find the next one. This is the fourth one at post. Yeah, so this is the fourth one, and look at, check these decimal places whether it is changes. Here you have 414 414 2121, right? But here 5, so here 569 21, here 356. Then you have to find another iterative to correct 8 decimal places. So if you find the next one, so here they haven't computed the next one, so you should do that, right? So, and stop this this process, this method, stop this procedure if you're so this is 1 2 3 4 5 6 7 8 9 10 11 12, but we need 8 decimal places. Is 10. So alright, this one, stop the criteria, stop this procedure, right? If the next iterative repeats the same numbers appearing here, right, then you stop that, then you stop the procedure, then you stop that one. Fine, stop finding next iterative. So right, suppose we get this number for third iterative and this number for fourth iterative, right? But these two are the same to 8 decimal places. Let's see. You look at these numbers here: 4 1 4 2 1 3 5 6. So this one is this one is same with this here, 1.4 1.41421 3 5 6. These numbers are exactly same with this one, so we can say that p sub 3 and p sub 4 are exactly same to 8 decimal places. Right, now we stop computing other iteratives, right? Now we code an approximation to that square root of 2 up to 8 decimal places. So this one is correct to 8 decimal places because the two consecutive iteratives are the same up to 8 decimal places. Then we stop our calculation, right? We stop calculating the next iteratives. So this one is an approximate value to square root of 2 up to 8 decimal places, right? So I hope you understood how to find an approximation to to any number of decimal places, right? So all you need to check is you have to check whether the two consecutive iteratives are the same up to which decimal places here. So these two numbers are the same up to 8 decimal places, right? So we stop calculating the next iterative. Then we found an approximation to square root of 2 up to 8 decimal places. I hope you understood how to find an approximation for the given accuracy, right? This approximate solution is accurate up to 8 decimal places, right? All right.